ladies and gentlemen, class recording has started. So today, that's probably not going to sound very good on the recording, but oh well. Today, we talk about momentum and impulse. And as you can see down at the sort of subheading of today's presentation, an extension of Newton's second law. So first, let's review. Newton's first law, we summarize with one word. What is that one word? Inertia, right? Suzanne, Newton's first law deals with things that do what? Not just stay still, stay constant, right? They either stay still or they do what? Move at a constant velocity, right? So Newton's first law deals with things staying the same, inertia, right? Newton's second law deals with what? What does Newton's second law do for us? Objects that, not just in motion, objects that change or accelerate, right? Newton's second law deals with things that accelerate. And over the past couple of days, we've talked about there are two factors that influence how much something accelerates. What are those two factors? Mass and net force, right? So mass and net force are those two factors. Now, there's another factor that we haven't discussed very much about, but it's important in terms of explaining what actually happens to an object in a situation, right? And that factor is time. For instance, how do I want to do this? We'll pick it up as we go along. Okay? All right, before we get to that time factor, let's do a couple of definitions. First, momentum. I think most of you have probably heard the word momentum, and you've probably used it before. If I asked you to define momentum, what would you say? How would you define momentum? Not necessarily in a physics sense, but just as you understand it at this point in time. Harris, go ahead.
Like a little force just so you can keep going.
Okay, it deals with like keeping going, right? Or building up in order to continue doing whatever we're doing, right? You know, so we talk about it in terms of maybe a heavy object has a lot of momentum, right? Or something that's going pretty fast has momentum, right? Would you agree with that, or yes, no?
Yes.
Okay, it was like you're just staring at me. You didn't like give me anything to say. All right.
I thought it was rhetorical.
Oh, so I was asking more for some confirmation to make sure that we. So when we talk about momentum, right? I've heard it described in a couple of different ways. I've heard it described before as a measure of an object's motion, and I'm like, what does that mean exactly, right? Because there's a lot of things we can measure about an object's motion, right? We can measure position, we can measure velocity, we can measure acceleration. All of those things deal with motion. I've also heard it described as inertia in motion, but inertia already covers things that are moving. Right? So I don't really know if I like that one either. Right? So let's just go straight up with our definition. Right? The instantaneous momentum of an object depends on its mass and its current, or what we refer to as its instantaneous velocity. First, when we talk about instantaneous, sorry, it's kind of messed up. As far as instantaneous is concerned, right? We refer to something as instantaneous. What does that mean? At any given moment or any given point in time, right? So when we talk about the instantaneous momentum, what we're dealing with is, that's fine. I'll just hear it. What is the momentum of that object at this very moment? Okay? Something that's going to be important later on today. Momentum is a vector quantity, right? Meaning it has to tell us two things, magnitude and direction. How much momentum does it have, and which way is that momentum going? So, instantaneous momentum depends on an object's mass and its instantaneous velocity. Baseball, tennis ball, right? If I throw them both with the same velocity, which one has more momentum?
Baseball?
Baseball. Why?
It has more mass.
More mass. Meaning, Mark, which one might be a little bit harder for us to catch?
The baseball?
The baseball, right? If we think about it in terms of the top two things up on the board, right? This baseball, if these two things are moving at the same velocity, this one might has more inertia because it has more mass, meaning it's harder for us to stop it, right? So, Eris, like we said, if we talk about something building up in order to keep going, right? This baseball wants to keep going more than the tennis ball does because it has more mass, right? So it has more momentum. Now, you might say, well, okay, that's just inertia, right? We've already talked about that, and that's true. But changing what an object is doing, now we can include another factor. So this idea of momentum actually comes out of Newton's second law. And earlier in this chapter, we defined Newton's second law as sigma F equals m times a, right? Net force equals mass times acceleration, which is true. But we know that acceleration depends on two things. What do we need to know in order to figure out the acceleration of an object? Sorry, let me rephrase that. In order to measure the acceleration of an object, what do we need to know?
Distance of time.
Not distance of time, that'll get us velocity. Top left-hand corner. Nah, that'll tell us how much it accelerates, but if we want to measure the acceleration of an object,
Velocity.
not just the velocity, the change in velocity and the time, right? Remember, that's how we define acceleration. Change in velocity over change in time, okay? So notice, before I talked about at the beginning that there's one factor that we've sort of left out in this situation, and that factor is time. Now, acceleration has a built-in time factor. That was good. It landed right on the desk right there. If we take that acceleration value, that equation for acceleration, or how we calculate the acceleration, we can plug that right into Newton's second law. Sigma F equals m times delta V over delta T. And then we do a little algebra, and we end up with this equation. Everybody follow that train of thought there? How we got from the top to the bottom? Everyone see how I went from the top to the bottom? So, that equation down at the bottom is just as important to analyzing the motion of an object as Newton's second law. Or analyzing, not so much, sorry, I should just say the motion of an object, the change in the motion of the object. And that's the delta part, right? This equation down at the bottom we refer to as the impulse momentum equation. Okay? Sigma F times delta T is equal to m times delta V. Sometimes we can drop the delta in front of the T and just say it's sigma F times T. That's perfectly fine. It's kind of the same thing, right? Okay, but sigma F times delta T is equal to m times delta V. Right? So the impulse momentum equation relates three things together for us. It relates the force acting on the object. I guess I probably should throw in another word in there, right? It's not just the force acting on the object. the net force, right? Because if all the force is balanced, nothing happens anyway, right? So the impulse momentum equation takes into account the force that's acting on the object and how long that force acts. That's the one factor that we really haven't considered up until this point. How much force is being applied to this object, but also how long are we applying that force? And then, taking into account both of those factors, how much does the motion of an object actually change? All right. Good with that so far? Okay. So let's take into account these two tennis balls. Let's say, to make our argument easier, both of these tennis balls have the same mass, right? So in that equation, we can say the mass of both of them is the same, right? I'm going to throw both of these tennis balls, right? Ready? Example number 1. Okay? Example number 2. Dirty window, apparently. I thought all that dirt was on the outside, but apparently not. So, all right. Everyone see, I don't know if you guys can see. Can you see the little spot that it left in the top left-hand corner of the window? The frame of the window might be blocking it for you guys, and for like Nick and Sarmat and Mark and Jeremy. But so anyway, all right. Obviously, a lot different with the first change in the motion versus the second change in the motion. So a couple of different things, right? One, what was different about my second throw versus my first throw? Okay, harder force, right? But there was another big difference too.
A smaller displacement.
On which one?
The second one.
The Mark, the second throw, where did I start it? Where did my arm start on the second throw?
It's farther back.
Right? And then it ended up over here, right? How long was I pushing the ball for?
Longer.
A lot longer, right? If I apply a greater force and I apply it for a longer time, what am I going to do to that object in terms of its velocity? Increase it, in this case. Could be decreasing as well, right? And we'll talk about that in a little bit, right? So, it's not just necessarily how much force you apply, but for how long you apply that force, right? If we talk about a rocket that takes off into space, right? A rocket, the engines on a rocket can supply a huge amount of force. And because of that huge amount of force, they can actually cause a very large acceleration, which is true. But if the rockets, or the engines on the rocket, only fired for 5 seconds, does that rocket end up in space? No. It would experience a very large acceleration, right? Because it has a huge force on it. But if you don't apply the force long enough, you don't actually get what you want out of it. Right? So this equation not only takes into account how much force we're applying on the object, but also for how long we apply that force. Because those ideas are, that's an important factor. And then those two factors together give us the resulting change in the velocity of the object that we end up with. Good there? This side of the equation over here, right? We refer to this side of the equation as the impulse. So the impulse of an object, or the impulse that is exerted on an object, depends on the force and the time. The impulse is equal to the change in an object's momentum. We'll talk a little bit more about impulse here in a second. The change in momentum of an object is equal to the impulse that is applied to that object. So the factors that we just talked about, that we just discussed about the amount of force you apply and the time that you apply that force, that makes up the impulse that we apply to the object. Impulse causes a change in an object's momentum. And it depends on two factors. It depends on the net force and the time that we apply that net force. So the impulse provided to the object is sigma F times delta T. How much force and how long do we apply that force? Both of those factors are important when we want to analyze the change in an object's motion. Like we said, a rocket engine can supply a huge force. And while it's supplying a huge force, it causes a large acceleration. But if that acceleration only lasts for a very short time, the overall change in an object's motion isn't very big. Large force, yes. Large acceleration, yes. But a big change in velocity, maybe not, because you just didn't apply that force for very long. Impulse takes into account how big of a force are you applying and how long are you applying that force. Good there. All right, let's go some practical situations. So flip it over onto the back. I'm actually going to skip around a little bit and not go in order. I'm going to start with this one. All right, so here is a time-lapse photograph of a guy swinging a golf club. Okay? So you can see that, that shows the position of the golf club at these different times. Let's say, like, each one of these pictures is, I don't know, a 1/100th of a second difference. I really don't know how much it is, but this is where the golf club is in each 0.01 second, right? But this doesn't just apply to a golf ball, it applies to a lot of athletic endeavors, right? Whether it's throwing a baseball, hitting a softball, hitting a tennis ball, kicking a soccer ball, anything that we do here, we usually talk about following through. That when you make contact with whatever it is you're trying to make contact with, you don't just stop, right? You continue that motion all the way through. Why? Well, if we first look at our impulse momentum equation, in the case of hitting a golf ball, hitting a baseball, throwing a softball, hitting a tennis ball, throwing a football, right? Generally, in all those cases, what do we want to do with delta V? Increase it, right? We want to make it as big as possible, right? Not always, but in a lot of cases we do, right? So, first, if we talk about this situation, the golf ball, does the mass of the golf ball change? No. So that factor remains constant the whole time. We want to increase this, right? This, the delta V, is on the right-hand side of the equation. If we want to make the right-hand side of an equation bigger, what do we have to do? Change the left-hand side. Specifically, do what, Suzanne? Let's talk about maybe not just increase the time, but also increase the force, right? Okay? So, if we want to make delta V as big as possible, right? That means we want to provide the biggest impulse that we can. Right? Impulse depends on two factors. What are the two factors that provide impulse to an object? How long you're applying the force and how much force you apply. So Connor, in order to apply a lot of force, what do? swing hard, right? You know, you work out, you build up your muscles, whatever it might be, right? But then, in the case of the follow-through, right? So if we look at this close up, with my hand playing the role of the golf club, and this ball playing the role of the golf ball, right? As we come through, no contact, no contact, no contact, no contact until we get to here. But if we continue our swing, right, that golf ball is going to continue or start moving forward as our golf club continues to move forward, right? So by following through, you're increasing the time that you're pushing on that object. Just like before when I threw the tennis ball, right, by taking my arm and starting it back here and following it through all the way to over in the front, right, I'm increasing the amount of time that I was applying a force to the tennis ball, right? So following through, we try to make sigma f and delta t as large as possible. Following through allows the golf ball and club to remain in contact for a longer time than they would otherwise. So in this case, we're trying to make delta V as big as possible. So in order to do that, we want to apply a big force, right? That's why we swing the club hard, or the bat, or, you know, when you're throwing something, right, you get stronger. But that technique allows you to remain in contact with that object longer, so we increase the impulse. Good there. Suzanne, can I use you as an example? Okay, so, first, before I use Suzanne as an example, right? Is everybody familiar if we talk about baseball or softball with a bunt? All right? Okay, good. All right, Suzanne, right? When you're bunting the ball, what do you try to do with the bat? Hold it kind of angled, right? Okay, and then just get the ball to hit it and drop, right? So, are you swinging? No. So you're not applying a lot of force, right? And you don't let the ball and bat be in contact for as long, right? So what does that do to the velocity of the ball then? Is it a big change or a small change? Small change, right? We don't apply as much force, we don't have them in contact as long, the change in velocity isn't as great. Okay? Another example. Okay? Ready? I'm going to jump. Okay? Ready? Here we go. Okay? That was impressive, I know. Right? So, if I want to jump higher, what should I do? Bend my knees, right? Because if I don't bend my knees, I can only apply a force, or the floor applies a force to me, only as long as it takes my ankle to bend, right, or to extend, right? That's all I got, right? But by bending my knees, right, now the floor is pushing on me the whole time that I'm extending my knees, right? And that increases the time that we're in contact with the floor, which in turn increases the time that the floor is in contact with us, which we'll talk about in a little bit, right? And that allows us to jump higher, right? Good there. All right, now let's flip it around and talk about the other way. Before we talk about the really morbid stuff, let's talk about this. Okay? All right, so top of the page. Here's a picture of two eggs that are falling. Let's say we drop these eggs from the same height. And let's also say that these two eggs have the same mass, although that really doesn't matter in this example. If we drop these two eggs from the same height, what should we see about them as they fall?
They're gonna be like the
Same height, and as they fall, they're going to
same acceleration.
same velocity, right? Because they're being acted on by what? Gravity. Gravity causes the constant acceleration for all objects. These eggs, really not a whole lot of air resistance with them, so we would see them accelerate at the same rate. Okay? Meaning that up until this point, right here, there is nothing different about the trip of those two eggs. Yes? All right. From the yellow line down, what happens to both of those eggs? They stop, right? So from the yellow line down, what would be the change in velocity for both of those eggs? Not necessarily a number, but how would they compare to each other? If they both stop, they're the same. Okay? Those eggs are stopping somehow, some way. Right? Regardless of how, they're both going to stop. But how we choose to stop them, obviously, has a big effect on what happens to them. Right? So let's talk about it in terms of our impulse momentum equation. There's our impulse momentum equation again. Okay? Now, in the last example with the golf club, what did we want to do with delta V? Make it big, right? But we just established that in this case here, what can we say is true about delta V for both of those eggs? It's going to be the same, right? So Mark, what does that mean about the right-hand side of this equation for both of those eggs?
It's going to be the same.
Exactly the same, right? So here's what I'm going to do. I'm going to, in this spot right here, M delta V, kind of in between these two pictures, because this delta V, M delta V is the same for this picture as it is for that picture. I know that's purple and it didn't show up very well, but it's the same for both pictures. Okay? Good there. All right. Two factors influence how we change the momentum. Those two factors being force and time. Right? So let's talk about the time. Here, landing in this nice cushy pillow. Relatively speaking, now if we talk about absolute time, it's not going to be that much. But relatively speaking, does it take a long time or a short time for this egg to stop? A long time, right? Because, now, granted, relatively speaking, right? It hits the pillow, right? And then the pillow cushions down as that egg falls into it. The whole time that pillow is bringing that egg to a stop. Right? Okay? But when it hits the plate, how long does it take the egg to stop? Pretty short time. Right? There's no give in that plate. It has to happen right away. All right? So, let's go here. Okay? We know that this M delta V has to be the same for both eggs. But, Mark, like we said, what do we know about the time for the pillow?
It's longer.
It's longer, right? So I'm going to make a big T over here, right? But for the plate, what do we say about the time? Shorter. So I'm going to make a little t over here. Okay? But that time isn't the only factor that affects changing the momentum, right? What other factor do we have to consider? The force. So, in the picture on the right, if we have a long time over which to stop this egg, how much force do we have to apply? We only have to apply a small amount of force. Why? Because we have a whole long time to stop it, right? But in the picture on the left with the plate, because we have to stop that egg very quickly, right? How much force do we have to apply? A lot of force, right? So in this case here, right, to summarize this, in both cases, delta V is going to be exactly the same. The change in momentum of both of these eggs is exactly the same, regardless of how it happens. When that is the case, and this is generally when you're stopping. We see this a lot mostly when something is stopping, because we know ultimately we're going to end up stopped. When that's the case, force and time have an inverse relationship. Not always, but in this specific case, where an object is coming to rest, force and time have an inverse relationship. Right? That being said, the pillow on the right makes delta T larger, which requires a smaller force. The plate on the left has a very short time to bring the egg to a stop, so it must apply a greater force. And as you can see, applying a greater force to this egg does what to it? Breaks it. So when delta V is the same, like I said, a lot of times that means when it's stopping. When delta V is the same, force and time have an inverse relationship. Two practical examples of this situation. Do you want the serious one first or the fun one first? Let's get the serious stuff out of the way first, then we'll have fun, right? Okay. So, this same application applies right here. Right? So, you're riding in a car, 35 miles per hour, and hopefully it doesn't happen, but it's probably going to happen to you sometime in your life. Right? Your car hits something. Another car, telephone pole, a fire hydrant, something. Your car feels a force. So what does your car do? If your car feels a force, it's going to what? Not yet. It's going to stop. But what are you going to do? You're going to keep going because you have what? Yes, but also another term we talked about earlier. You have momentum, but you also have inertia. And Jake, inertia is part of momentum, right? So you have inertia. You keep going, right? Until you run into something that makes you stop, right? The airbag does exactly the same thing that the pillow did in the previous example. In the airbag, relatively speaking, how long does it take you to stop? A long time or a short time? A long time. Relatively speaking. Not in real life. If we look at actual time, it's actually very short. But it's a lot longer than, say, the steering wheel, or the dashboard, or the windshield, right? So in this case, right, the airbag and in conjunction with the seatbelt, right, those things increase the amount of time it takes you to stop. In this case, because regardless of how, eventually what are you going to do? You're going to stop eventually, right? That case, right, same as the egg before, right? You don't have to write all this down, because if you write all this down, we won't get the fun example at the end, right? But delta V is going to be the same, and that means force and time have an inverse relationship, and therefore the seatbelt and the airbag make the time longer, which requires a smaller force. Now, is it like jumping into a big cushy bed? No. Right? If you've ever seen it before, right? Or if you've ever known anybody who's been in an accident where an airbag has deployed, right? A lot of times they will end up like a seatbelt too. A seatbelt will leave a big mark across your chest, right? And sometimes it'll cut your shoulder, and like they'll leave like the airbag will leave like scrapes on your face and stuff like that. But right, because it's not a long time that it takes it to stop you, but it's longer than the steering wheel, right? So it still has to apply a relatively big force, but it applies less force than the steering wheel would to stop you. Good there? All right, let's do a more fun example, right? So hopefully in a couple weeks, or maybe a couple months, whatever, you're going to go to a family reunion over the summer, right? You're going to have good old fun time doing the water balloon toss, right? Yes? Come on, Suzanne. Tell me you've never done the water balloon toss before. All right, so we're doing the water balloon toss, right? How do we catch the water balloon? What do you do when you catch the water balloon, right? Like this, right? You give it the old cradle like that, right? Why? What does that do?
So the motion of the balloon keeps going.
Yes. What are you doing to that balloon, Eris? You have to do what to that balloon? You have to eventually stop it, right? That balloon's going to stop somehow. Whether you catch it or whether it hits the ground, it's going to stop, right? By doing that cradle, you're increasing the time, which does what to the force? Decreases the force, right? All right, see you guys tomorrow for Newton's third law. Woo!